Hello, everyone. Welcome to the introductory lecture of the mini course on what is computation, from Turing machines to black holes and neurons. So what is computation? Maybe when it comes to computation, the first thing you come up with is something like, oh, maybe the digital toothbrush I use every day, there's a computer inside. And maybe you think of, oh, the spacecraft itself also have some supercomputer insides. And maybe you'll think about your phone. Okay, maybe not this kind of phone, like the smartphone you have. There's also computer inside. But maybe there's also beyond that. For example, your cat maybe has a toy. It's a digital toy, and there might be also a computer inside to play around with him. Yeah, but sadly for my cat Shiba, he doesn't have that kind of fancy toy. But his toy actually is myself. It's me. And I also have a brand, and this brand also kind of is doing some kind of computation. And now maybe some mathematician will jump up and say, oh, no. Actually, when you say computation, yeah, you are saying Turing machine. But for normal people, when they heard of Turing machine, they might feel, oh, what's that? But when they look at mathematician, they will think, oh, you mathematicians are also doing some kind of computation. And then physicists might jump up saying that, oh, actually from the smallest things in the world, like the particles, and to the largest things like in the world, like in the universe, like black holes, they are all doing certain kind of computation. So it seems that there are so many things like related to computation when we talk about it. But wait a second, speaking of computation, what do we precisely mean? So maybe let's go back to the examples we have brainstorming in the beginning. Yeah, and let's try to take a step back and try to abstract out the unifying things of all these examples. So for the first things we might come up with, those are maybe related to technology. Yeah, those are like the digital computers in all sorts of different forms in our daily life. And for the second categories of example come up with, maybe this related to biology, like our brain or even my cat's brain is doing certain kind of computation. And for the third category is related to math. These are like a formal and rigorous methods that reason about computation. And finally, it's about like the physical worlds. And you can come up with even more, like lots of different subcategories of lots of stuff. They all seems to involve certain kind of computation. But this might be too much, and we can keep going on and on. But this won't end anywhere, and we need to get started. So maybe let's stick with the four or like even just the three big categories we are looking at. And in this and to study the computations related to all these different categories, maybe there are two directions we can study. The first is like, oh, how does computation plays a role inside each categories? So it's like in technology, it's like, oh, computation is like in the form of computer. And in biology, it's like, oh, our brain is doing computation. In the meantime, and maybe this is actually more interesting to this mini course, we can also act in the other direction. Yeah, for all these different examples of like intuitively related to computation, yeah, how can this help us to think about or like to reason about the definition or the concept of computation even better? In the sense that like through, for example, through biology or through physics or math, there are different intuition or computations. Can we abstract them out and help us to think clearer about the definition of computation, or even like reframe it in a more modern way? So I hope this already gives you a feeling that, oh, computation, yeah, actually maybe it's actually beyond technology. It can be a very interdisciplinary notion. Yeah, and you might say, okay, so okay, maybe I believe in Chi-Ning, but so what? Yeah, why should I care? Yeah, and yeah, actually you don't have to care. But in this mini course, I would say if you have one of the following, like the curiosity in knowledge, patience in learning, love to have a deep and broad thinking, and like a wide ranges of interest, then I sincerely invite you to re-examine the essence of computation together in this mini course. So yeah, so welcome to a journey of the cross-disciplinary exploration with me. So let me start with an overview on this mini course, and although this is an online version, but yeah, if you have any questions, please ask like in the comments on YouTube. So maybe let's start with a brief introduction of myself. So I'm Chi-Ning. I'm a fifth-year PhD student at Harvard, advised by BOSS. Yeah, and my original research field is theoretical CS, but I'm also widely interested in like math, physics, and biology, especially the interactions between theoretical CS. And yeah, this is, and on the right, this is my cat Shiba. Yeah, he will be like a central example or like a main in this mini course. So as I mentioned earlier, this course, we are going to re-examine the notion of computation through a more abstract approach. In particular, we are focusing more on the direction of trying to rethink about computation from different areas, including biology, math, and physics, maybe a little from technology. In particular, we are going to have 3 modules: mathematics, physics, and biology. And before, I really explain the details of these 3, maybe you should ask a question first, like why these 3 areas? And I'm going to convince you why these 3 areas are related. And moreover, I want to explain to you like the 3 areas actually think quite differently. And I hope through this mini course can also help you to have a feeling about like the taste and the flavor of these 3 different areas. So first is math. So when it comes to mathematics, maybe this is what people will have in mind. There are like lots of fancy and complicated calculations on Blackboard. Yeah, but actually in this mini course, I want to emphasize that mathematics actually is a general language and a universal language for us to communicate. Through this language, actually, we can think even more freer and in an abstract way. So maybe like in the beginning, like what people will probably have first in their minds, and mathematics might have lots of rules, calculations, and complicated construction notations, which makes people feel very scared and don't want to touch math. For example, in this background, it is actually a screenshot of my very own paper. Yeah, sometimes even myself as a theoretician, when I do like a very complicated calculation, I also don't really like it. But I want to emphasize that mathematics in a very high level, if you're not mathematicians or you are not a theorist, you maybe don't really need to do all the details. But mathematics can still like help you a lot in a sense that it can help you to think in a very abstract way and maybe guide you to find some new observations. So I encourage you that even though you might not very familiar with math, but maybe in the mathematical modules, I encourage you to follow the instinct and feeling, yeah, when you watch the lecture, and think of like watching those lecture as like watching a movie, like watching an art movie, and trying to just have a feeling of the underlying story. So in this mathematical modules, we are going to have 3 lectures. The first is about some fundamentals concepts of how people study computation through mathematics. We will start with like how people have a formal definition, like a formal language to capture what a computational problem is. And then talk about something called Turing machine, which is in the title of this mini course. And talk about how people postulate Turing machine as a mechanical procedure, so that when they want to study mechanical procedure or algorithm, they can instead just study the mathematical abstraction Turing machine. And in the second lecture, we're going to talk about some modern approaches people study computation in the mathematical way. Yeah, for example, we'll talk about lots of different computational models beyond Turing machine. And we are going to talk about different computational resources being modeled in a mathematical way. and we are going to talk about complexity classes, which is the way people study like how different computational resources play around with each other. And we're also going to talk about central idea co-reductions in the modern approach. And this might also be useful for your other, like either your research or your like daily thinking. And finally, we're going to talk a little bit about some philosophy of like how the mathematical study of computation connected to the reality, for example. Okay, so the second module is about physics. So why physics? So as I mentioned earlier, in mathematics, one of the advantage is freedom. It gives us a very abstract and very general language for us to study the object we're interested in. And to me, physics actually is kind of in the other way. Actually, because in physics, people study like the nature world around us, the physical world. And the physical world will give us some constraints and structure when we observe it. So we cannot have an arbitrary model or an arbitrary understanding to the world. We need to abstract out the real physical world to like maybe a mathematical simplified model, but somehow still captures the essence of the physical worlds and can tell us a lot about things about it. So in physics, it's more about like identifying constraints and then identifying structures and have a good abstraction and capture the symmetry. So in the module of physics, I encourage you, if you are not familiar with physics, it's totally fine. I encourage you to focus on like different worldviews and postulates like physicists has been used for like a different way for them to model the physical world. So in this module, we are going to also have 3 lectures. In the first lecture, we are going to talk about some classical approach physicists study the physical world. We start with like Newton's law and its connection to like computation. We talk about classical mechanics and statistical mechanics. And in the second lecture, we're going to also talk about something more modern. We talk about like quantum mechanics, yeah, and like how quantum mechanics inspire 2 different approaches to do quantum computation, called quantum circuits and adiabatic quantum computation. So this is like a very modern and hot topics, and I also want to hope I can clarify a little bit. And finally, we'll briefly mention the connection between black holes or like a gravitational theory in general to computation. In the third lecture, we're going to talk about some philosophy, like on how can we, how's the computational view can help us like understanding the physical worlds and etc. So finally, in the third module, we're going to talk about biology. And at least from the audience in the mini course, yeah, most people are actually coming from physics or math background. Yeah, the least number of people are coming from biology. So when it comes to biology, some friends often like to joke to me like, "Oh, biology is a field of like collecting stamps." And to me, I feel like it's actually even more. I mean, it's actually beyond that. And to me, it's actually study biology is very similar to one of my favorite board games, Jigsaw Puzzle. So what do I mean that? So in biology, it's slightly unlike physics and mathematics that people usually can have a very general and universal word for the objects they are studying. In biology, due to the lots of special examples and noises in the experiment, etc., usually people can only collect evidence one by one. So it is really like in Jigsaw Puzzle, you collect like one pieces by one pieces. And this is also difficult in the sense that, for example, in this Jigsaw Puzzle I played last summer, when you in the beginning collect maybe lots of orange pieces, you might think that, oh, they are all orange, so maybe they are related. But after you collect more and trying even more, you will realize, oh, actually they might actually belong to different cats. Yeah, some are actually together, but some are not. So is that in biology? this kind of lake of big picture is a challenging part and is also a confusing part, but also its beautiful part. It is like through collecting evidence and small pieces, gradually you will see the big picture better and better. So in this, in the biology module, I'm going to talk about lots of examples. And I hope when you are looking at those examples, you can just think of it as building up your own story to like fulfilling like the big picture of the jigsaw puzzle you are playing. So in the biology module, we're also going to have 3 lectures. So in the first lecture, I'll give lots of examples, and especially this 5 different examples of how computation connects to biology. And in the second lecture, I'm going to focus on 2 mysteries, evolution and brain, and their connection to computations. So we'll start with talking about the essence of natural selection, which is one of the central theory in the study of evolution. And we are talking about like different examples and see how evolution can be a computational principle. And then we are going to talk about neuroscience or brain. And we also have different examples in different layers, different levels of the brain, and trying to convince you that actually in the brain, there are lots of different computational notions, but it's also very complicated, lots of different intuition and idea about computations. They might mingle together and make it a very difficult area to study. And finally, we're also going to have a philosophy lecture talking about like what would be the difficulty of study biology and how can the computational view potentially help and what's the future direction we can hope for. So maybe now having an overview of the 3 modules, let you have a little sense about what's going to be covered and why they are slightly related to computation. But you might have a question that, oh, but why these 3 and why to put these 3 in parallel? And are there any really intersection of these 3 different subjects when we talk about computation? So in this slides, I'm going to give you an example. Actually 3 examples, one in each field. And I want to convince you that those 3 actually all have similar flavors, although they are phrases in different way in their field. And hope this example can convince you that it is really worth study the computation notion using like very different approaches, because different fields, they actually might have very similar ideas. So in the mathematics part, I'm going to talk about the example of one-way functions. So what is one-way functions? We are going to, And in the physics part, we are going to talk about chaotic phenomenon. And in the biology part, we're going to talk about emergence properties. So what is one-way functions? So the idea of one-way function is the following. You might have 2 different inputs. Maybe both of them are actually the photos of my cat Shiba, but they are slightly different. And when you feed into a one-way function, and in this example, I call it a hash function, which is a special case of one-way function, then the result will be completely different. Even though in the beginning, they are actually all both are photos of Shiba, but because they are slightly different, the result actually could be completely different. And moreover, this is called one-way because it is very difficult for you to invert the output of the hash function or the one-way function back to its original input. And in physics, there's this notion of chaotic phenomenon, which also known as the butterfly effect. So it is saying that if the initial physical situation may be slightly different in the sense that in one world, the butterfly did nothing, and in the other world, the butterfly may be shattered a little bit. And after the physical world runs their physical laws, it can result in very, very different reality or the result. It could be a case that, oh, Boston is having a snowstorm, or it could be a very good weather. But it's just slightly different in the beginning can cause very different things in the end. And it's also saying that if you know the result, it's also very difficult for you to understand what's the initial configurations. And finally, in the biology part, this is the emergence properties. So the example I'm going to give, maybe it's not the super good example, but intuitively, this also make the analogy more similar. So the example I'm going to give is the following. It's like, for example, the genes I have and the genes Shiba as a cat have, actually phylogenetically, they are very similar. Yeah, like if you're just looking at the gene types, yeah, we are actually maybe like 90% or even more similar to each other. But because of the arrangement are different, etc., after the development of the biological words, the biological laws, it can result in very different things. Yeah, one can result in me and the other resulting in Shiba. And similarly, just knowing like the end result, you are also, it's also very difficult or nearly impossible for you to know what's the initial genes I have. So I hope this slides give you a rough sense that, so all of them, like one-way functions, chaotic phenomenon, and emergence properties, they are all central objects in the study of each field. And they care about, I mean, maybe different aspects. For example, in one-way function, people care more about the difficulty of inverting. And chaotic phenomenon, people care about the small difference in the initial situations, make the result unpredictable. And maybe in emergency property, people also care about like the input and output, like how can output be so diverse and so have so many different patterns. So all these three areas maybe care about things differently, but the underlying mechanisms are very, very similar. So by studying all of them, this can potentially give you a different angle to view the same things from like different fields, and potentially this can be a flourishing direction. So I hope this is also going to be the central theme of this mini course. We are going to talk about very interdisciplinary stuff, like all from like math, physics, and biology, and hope through different angles can give you like different ideas to view the same thing. So in this mini course, we're going to talk about the connection between computation to math and physics and biology. Especially, we're going to use lots of examples and the stories to give you ideas. And in the end, I also hope I can help you to build appreciation of how different fields study and approach problems. But of course, due to a limit of time, we can only cover very, very small part of it. And there are lots of things that we actually cannot cover. For example, like consciousness, creativity, intelligence, etc., or like information theory, game theory, cryptography, learning, etc. And but I want to use this quote maybe to, to encourage people, because our knowledge can only be finite, while ignorance must necessarily be infinite. But the way to interpret this maybe is like, oh, in the end, still a finite being, we cannot really learn everything, but we still need to start. So I hope this mini course at least give you a start to like think about computation through like 3 different angles. Although I'm going to all focus more on the high level settings, but hope to give you the basic stories and the basic appreciation so that you can pursue your further study. So I know, like for the audience, you might coming from very different backgrounds, and for some lectures, it might be very easy for you, and some might be very foreign to you. So if you are familiar with the materials, I encourage you to maybe focus more on the high-level pictures and see how I give the narrative. And maybe you can also think about how to explain the materials to others, and this might also help reshaping your own understanding. And if you are unfamiliar with the materials, I also encourage you to also focus on the high-level story, because it's probably very difficult for you just like using like few hours to really grasp all the details. But at least like through these high-level stories, it can it can be a starting point for you to do further study. You can know what materials you are going to dig into further later, and also know roughly about like what people in the different field appreciate things. So I think in either case, yeah, you should feel comfortable. Yeah, I mean, like when seeing something either too easy or too difficult, yeah, this is intended to be like this. And the point is really about like giving you the exposures and to inspire your further study. So the goal of this mini course, as I keep mentioning so far, is to provide you like a ground to think about, rethink about the notion of computation through three different fields: mathematics, physics, and biology. Especially, I want to focus on the appreciation. So people often ask me like, oh, Chi-Ning, you do so many interdisciplinary research and studies. What kind of, what's the most difficulties you encountered? And many people actually would guess, oh, is that the language barrier? Because like each field, they might have a very different way to talk about their own stuff. They might have lots of jargons and make it very hard for people not in their field to understand. And indeed, this is difficulties. But actually, after like learning all this like biology and physics for many years, and although language is a problem indeed, but I realized a more difficult or a more implicit challenges is actually appreciation. Because different fields have different appreciations. And if you use the appreciations from your own home field, sometimes it's conflicting with the appreciations of different fields and make it very difficult for you to know why some result is regarded as important in other fields. And maybe this is a little bit abstract, so let me use an toy example to convey this idea of different appreciations could be a barrier. For example, this is Shiba again. And some people, maybe when seeing Shiba, their appreciation to Shiba is like, oh, Shiba is so cute. And maybe for some other people, they actually maybe don't think Shiba is cute, but they think, oh, Shiba is so smart. Yeah, and for some people, for example, physicists, maybe they will think, oh, no, I think Shiba actually is dumb. I actually like Schrodinger's cat better, if you know what that means. And maybe for mathematician, they even don't care about this. They care more about maybe like an abstract word. They might say, oh, can you axiomize Shiba? If so, maybe I can take care of Shiba when you're on vacation. So it's like for different people from different training and different background, when they look at the same things, they might have totally different feeling. And it is very difficult in the beginning to really understand why people from other fields appreciate the same thing in a different way. And in this mini course, I actually hope I can bring the appreciations of different fields all in front of you to at least let you know that how people in other fields appreciate things. And this is not saying that you should change your own appreciation, but instead, I hope through this mini course, it can help you know at least know that those different appreciation exist, and you can think about like if you want to adjust or not, or at least you can respect what other people appreciate things. So in this mini course, we are going to talk about mathematics, physics, and biology and their intersection to computation. And as I mentioned earlier, this is a short lecture, so I definitely cannot cover too many things. And this is just going to be the beginning of a lifelong journey for you. So here are some quick logistics. Yeah, and since this is an online version of the lecture, so I'm going to skip this part. But for the rest of this introductory lecture, I'm going to talk about like what's our guest speakers, and you can find all the recordings in the YouTube playlist. So for module 1, we are going to have a guest speaker, Li Jichen from MIT. He's going to talk about like the efficiency of algorithm and Sourite paradox. So this is like Lija is going to use some paradox, the Sora paradox from philosophy, to argue about the legitimacy of like how modern theoretical computer scientists study the efficiency of algorithms. So this is a more philosophical talk. And for the second module, we're going to have two guest speakers. First is Chi-Ning, going to talk about quantum correlation. And in fact, actually, this lecture is recorded, but this is not made public. If you are interested, please email me and Chi-Ning, and we can give you a link. And finally, Sona is going to talk about quantum machine learning. And unfortunately, because she's mentioning something related to the frontier research she's doing, so this talk is not recorded. But if you are interested, I also encourage you to maybe send an email to Sona or me, and then maybe we can see if you want to share the slides with you. In the third module, the biology module, we are going to have three guest speakers. First, Angel is going to talk about creativity, and Zichen is going to talk about art, and Praviba is going to talk about intelligence. So all these three things are like maybe they're all slightly related to computation, but also related in a maybe slightly more unconventional way. So in all three guest lectures, it's going to like trying to explore what can we think about like those different topics, the creativity, art, and intelligence through the lens of computation and beyond. And finally, we are also very fortunate to have lots of students volunteer to be teaching staff, and thank you so much. And especially like eight of them actually provides like lots of advanced sections, trying to complement the depth, like to make this mini course deeper. Yeah, and all of those advanced section were recorded. So I also encourage you to go to the YouTube playlist and to check it out. Yeah, so finally, yeah, this mini course also have you. You as an audience is also part of the mini course to help us to have inspiration and learn together and explore together. So even though maybe you are watching this video now, you are not in a mini course, but I still encourage you to engage in a way that maybe leaving some comments in the YouTube, or maybe send me an email, and hopefully, yeah, on this journey of study computation through interdisciplinary approach, we can all have some inspiration for each other. Okay, so this is the end of the introductory lecture. I hope you enjoyed and also enjoy the future lectures of this mini course. Thank you for your attention.